I usually start analyzing tool life and insert failure with asking my students, how many of you have kids? Something tells me that wouldn't be appropriate for this class, would it? All right, but the reason I bring this up, how many of you have kids? All right, you do, the instructors do, because cutting tools are just like children. I have 3 sons. If I ignore one of my 3 sons, if I don't listen to them, what happens? They get problems. They get into trouble. When kids are babies and it gets quiet, that's when you know you have a problem. Inserts are just like kids. Cutting tools are just like kids. If you pay attention to them, they will tell you exactly what's wrong. They will tell you exactly why they fail. And if you know how they fail, what can you do? You can fix it. You know exactly what to do to fix it. And this section is in your book. It's the failure analysis. When you look at tool failure, let's be honest with you. What I make, cutting tools, another name for them in the industry is perishable tooling. It is supposed to wear out. Perishable. It's like milk. Keep it around too long, it wears out. This stuff does too. You use it too long, it wears out. But here's the ticket. You want it to wear out on your terms, not on its terms. Right? So, what you really want to happen is abrasive wear. And what really happens, before we go any further, let's see if anybody remembers this. Be careful. All be careful. Well, I wondered what the world is this guy doing? Jimmy Neutron. Okay, I can go with that. What is it? It's an atom. What's in here? What's this called? That's the nucleus of the atom. It's made up of protons and neutrons. What's out here? Electrons. What do we know about electrons? What happens to electrons when they get hot and bothered? They go fast. They go fast. And what do they want to do? They want to bounce around, and when they get really hot and bothered, not only do they want to bounce around, they want to bond with something. They want to bond with something. And here's the truth. There's 3 basic elements in carbide. Tungsten, carbon, and cobalt. What is the basic building block? What one of those 3 elements is the basic building block of everything in the world? Carbon. And the reason that carbon is that basic building block is it has a lot of electrons out here. It bonds with everything. Now, if carbon, it is in my cutting tool. How many of you have ever heard of high carbon, low carbon steel? Right? It's in all the materials that we machine. How hot is it at the shear zone? 12 to 1400 degrees Fahrenheit. Those electrons are pretty hot and bothered. When carbide wears out, it is actually a chemical reaction. The electrons in the carbon in the insert dissolve into the carbon electrons in the steel. They actually bond together. This dissolves and goes away with this. We call it abrasive wear, but it is actually a chemical reaction that's taking place. You control that through your heat and pressure. I want flank wear. Flank wear is my friend. My tool's going to wear out. If I have flank wear, I can control it. Then there's 2 other types of failure mode groups, heat failure and mechanical failure. Under heat failure, I got something called built-up edge. I've also got something called thermal cracking. And then I got crater wear, and then my favorite, thermal deformation. Reminds me of the DC comic character. Doesn't work with them either. I need to throw that one from my repertoire. When you look at mechanical failure, I've got chipping, and there's there's three types of chipping. I can get flank chipping, rank chipping, or I can get just chipping. And then I got depth of cut notching, and last but not least, I got my favorite one, it broke. I used to run the quality department for another manufacturer of cutting tools. I would get cutting tools back in pieces. They would ask me, what is wrong? You know what I would tell them? It broke. Typically, I had no idea what happened. You know why? The evidence went into the chip conveyor and out and was sitting in the hopper. Usually, when it gets down here to it broke, one of these other things was happening, you weren't paying attention to it, and it broke. Okay, so let's look at these. Flank wear. First of all, what color is wear? On a cutting tool, what color is wear? Doesn't matter what color it is. No. Everybody thinks wear is black. The first thing you need to understand, what is the wear stuff, what is the black stuff on your cutting tool? Carbon. It's the crap in the steel, in the coolant. It's just carbon buildup. It's not wear. Silver. It's the silver line, and here's the truth. Most of our inserts, we would prefer them to be black. They don't need to be gold. Actually, it costs us more to make them gold. But people always think wear is black, and they won't buy a black insert because they say they can't see the wear on a black insert. Actually, if you're looking at real wear, which is silver, silver shows up better on black than it does on gold. It is silver. It is a silver line that starts on the cutting edge and goes down the flank. So if I look at the flank on an insert, if this is my rake face, it's the adjacent surface. If it's my tool, drill, here's my cutting edge, it would be on the clearance face. That's where you see the silver line. That's what you're seeing right here. It's a silver line. Here it is on a drill. That's on an insert. On an end mill, it would be back here on the side. This, if you measure this is about 8 thousandths flank wear. Okay? That's what it is. It's a silver line. A lot of times it's bigger around the nose of an insert. And the reason being, if I'm feeding 10 thousandths feed rate, my chip is 10 thousandths. Let's say this is 10, it's that thick. But as I go around that nose radius, that chip thins out. Where it thins out around that radius. And if the chip's thinning out, where's the heat going? Into my cutting tool, so it wears deeper. So that flank wear, a lot of times when you're looking at a cutting tool, when you're looking at that cutting tool, that flank wear will be deeper like that around the nose. And usually, actually, oh my God.
I was going to say, nice. Permanent marker on a dry erase board.
Oh, I did the whole thing too, didn't I? That'll be fun. It'll be clean tomorrow. All right, anyway, it gets thicker around the nose of the insert, which is what you see here, than it does around the cutting edge. You want to spray it? I'll let it go. Let it go. All right, now here's the truth. Everybody asks me, how much flank wear should I have? And really, it's up to you. Whatever your insert thickness is, typically 10%. So if this is a 187 thick, 18 to 20 thousandths. Now as that starts wearing out, what happens to the size of your part? It either gets bigger or smaller, depending on if you're on the OD or the ID. We say for finishing, 5%. The only reason we reduce it in finishing is because you don't want to have to change your offset as much, because as your tool's wearing out, you have to change your offset to hold size, right? Okay. Now, flank wear, when I say flank wear is your friend, I really truly mean it. There is a facility that makes surveillance cameras. Most of you don't realize it, but you are photographed on average 75 times a day. In a normal day. On this campus, it's even more often than that. Normal day when you go to school, walk out of your house 75 times a day. Realize that. Big Brother is watching. This company makes a lot of cameras. They run lights out. Their whole factory. When they turn on the machines, there's no people there. They have people that come in, they load the machines, they load cutting tools, they turn out the lights, they push the cycle start button, and they go home. They run totally lights out, unattended. They make tens of thousands of these cameras a day. And the reason they're able to do it is because flank wear is predictable. They've run this type of chart. What happens if you look at time and you look at wear? When you put a cutting tool in and you start cutting, in the first 5 minutes or so, in the first few minutes of cut, it breaks in. It wears pretty quickly. That wear land will grow to about 5/1000 of an inch. We call that the A zone. This area would be the A zone. Now this second area here that we call the B zone, usually is a little bit flatter. And what I mean by that, usually I get that rapid break-in, and it's a little bit more of an angle, and then it goes here. That one over there is a little bit flatter. So this is my A zone, this is my B zone, and this I call my oh no zone. Because once I get out there, I don't know what's going to happen. This area here, this is the break-in zone, and what I call this is the constant wear zone. I mean, you have steps in your house or leading up to your house. You know with steps you have what they call a rise over run. Every step has to be the same height versus width. The state codes are really picky about that. That's the same thing that happens in this zone. What I mean is for every so many minutes of cut, I get the same amount of growth of wear. For the same amount of minutes, I get the same amount of growth. For the same amount of minutes, I get the same amount of growth. It's a constant wear zone. Flank wear is your friend. I can play with that zone and lengthen or shorten it based on what I do with my speed. Because speed is heat, and that's what controls it. That's why I want this flank wear as my failure mode and none of the others, because I can control it. It's the only failure mechanism that I can actually control by just playing with the speed. It produces consistent tool life. It allows me to optimize my operation. I can extend it by playing with my speed or getting a harder grade of carbide. Harder, more like glass, takes more heat. Now, let's take a look at heat failure. I got something called built-up edge, I got thermal cracking, I got cratering, and I got my favorite, thermal deformation. Built-up edge, it's simple. How many of you ever seen when you're machining soft gummy steel or an aluminum, it builds up on the cutting edge. You get a little booger on the edge, right? What happens when that booger grows so big on your cutting edge? Eventually what happens to it? It breaks off. What does it do when it breaks off? It takes the carbide with it. And then built-up edge looks like a chip. Or it could look, built-up edge could have turned into it broke. Or it could look like it notched. But it started off as built-up edge. So, the definition of built-up edge is when the material you're machining cold welds itself to the face of the insert. If I'm cold welding, what do I not have enough of? If I'm cold welding, I don't have enough heat. I'm not plasticizing the chip. What two things does it take to make a chip? Heat and pressure. If I don't have enough heat, I'm not plastically deforming my material, and some of it's sticking to my rake face. Okay? I don't need that. I need more heat. So let's take a look at it. This video is kind of hard to see. I'm going to run it a few times. Now what you got going on here, don't pay attention to this side right now. Right here's where the cutting tool is. You see the part that's not moving here? Right here is where my built-up edge is forming. I'm going to run it again. And eventually this built-up edge, this is my cutting tool here. That's the built-up edge, that's the chip. You see the build-up fall off there's my cutting tool. Now you can see what I'm talking about. Watch the built-up edge start building up here. Builds up, builds up, builds up, builds up, builds up, builds up, builds up. All this is built up edge. That's not the cutting tool. The cutting tool is way back here. See where my cutting tool is? And that's because I'm not running enough heat. So what do? Speed up a little bit. The other thing you need to remember when you're getting built up edge on your cutting tool, if I'm getting built up edge on this, I flip it over, I better first take this insert, this edge that has the built up edge on it, and rub it on a piece of sandpaper, clean it off, flip it over before I put it back in. Because if that built up edge hits my seat before the mounting surface, my insert's going to rock. Okay, so for built up edge, it's pretty simple. I also may want, would I want more negative? Remember my negative and positive earlier? Remember when I had the negative cutting tool, which was shaped like this, and then I had the positive that was, well, that wasn't a very good drawing. More like that. Which one's going to be freer cutting? This one. This could almost also help. That is built up edge on an insert. As it builds up too much, it breaks off, it takes the whole thing. I can use a higher speed. We haven't talked about PVD coatings, but PVD, physical vapor deposition, is usually put on dead sharp edges. I could use cutting fluid. Gives me a little bit more lubricity, but I only like cutting fluid in turning. I do not like using cutting fluids in milling. I will talk about that in a minute. If I get too much flank wear, this edge gets too dull, it can start building up as well. Not only can I get it on the rake face or the top of the tool, sometimes I can get that build up here on the clearance. If I have a boring bar and it's deflecting, it starts rubbing on the clearance. Does that make sense? I get that built up here instead of on the top. As I get that buildup keeps building up, eventually it pushes too much on the tool and the top pops off. On the CD, they have the formulas. On your CD, there are several Excel files. In those Excel files, there are formulas. What I mean, boring bar deflection. When you cut something with a boring bar, it's going to deflect. It's physics. But if you know how far it's going to deflect, you can actually raise it. Because you always want to cut on center, right? If you know how far it's going to deflect, you can raise the tool so that when it deflects, it's back on center, right? That formula is in there. All you got to do is put in numbers. This is my boring bar diameter. This is my depth of cut. This is the type of material I'm machining. It's automatic. It'll give you the answer. So, if I've got that flank build up, I increase my primary clearance angle. I can actually give it more, make it more positive. I can increase my feed rate, or I could decrease the size of my hone. Now, we didn't talk about this because that's actually in the middle of your book, but every cutting tool, if you look at your desk, look at this desk. If you look on this side, this edge of this desk is very rounded, right? If you look at this edge, it's not, right? That's edge prep. Why do you think we put this nice big edge prep here? So you wouldn't rub up, it's more comfortable, right? Okay? Here we don't care. We change the edge prep from this to more dead sharp depending on the material. And what edge prep does, everybody thinks it dulls the cutting edge, therefore protecting the cutting edge. But let's say I have that type of radius, or I have what I call a K-land, or I have edge sharp. The one thing I know, cutting forces are always what to the cutting edge? Perpendicular. When I have this big radius, I have an infinite number of perpendiculars. All my cutting forces are going into the compressive strength of my tool. Make sense? That's why I put it. Here, they would be going in this direction, again, into my string. Here, this whole thing is going to want to pop off. Just like that. That's why we put edge prep on inserts. Thermal cracking. What happens when you put hot water on a cold windshield? It cracks. Milling. How hot is it at the shear zone? 1200 degrees. Now when that insert in the milling cutter is in the cut, it's 1200 degrees. When it comes out and you put coolant on it, what do you think you're doing to it? When things heat up, what happens? When they cool down, what happens? In milling, your insert is already heating up, cooling down. It's getting hot, cold, hot, cold, hot, cold. It's growing, shrinking, growing, shrinking, growing, shrinking, growing, shrinking. You put coolant on it in between, what do you think you're going to do? You're going to shock it. You will actually get these cracks. They're called cone cracks. That constant expansion, contraction, expansion, contraction, expansion, contraction will literally rip the insert or the cutting edge apart. Now, oops, here we go. Of the three basic elements in carbide, which one do you think I put more in to absorb that expansion, contraction? Cobalt, marshmallow. If I put more marshmallow in, do I go faster or slower? This is counterintuitive. Everybody thinks if you're running a graded carbide that can run wet, you're going faster. But that's wrong. Carbide that you run wet must have more cobalt. Cobalt melts. Marshmallow melts under heat. Every manufacturer of carbide, their carbide grades in milling that they say to run wet, you have to run them at slower surface finishes. A lot of people don't realize that. The grades that you run dry, you can run faster. That's counter. So here's the truth. I cut the coolant off. 90% of the time I get 30% more tool life in milling. Now there are times I have to run coolant. Stainless steel, sometimes to get a good surface finish. High temperature alloys, you have to run coolant because they just don't, you can't, your tool will never last if you don't. Sometimes cast iron to keep the dust down. But a lot of time you can run faster speeds and get better tool life without coolant in milling. True story. A lot of people use coolant in milling in order to get the chips out of the way. You're starting to see more manufacturers of CNC machines putting air blast, right? You're seeing it come through the spindle even, right? Yep. In some cases. They weren't that way 3, 4, 5 years ago, were they? Maybe 10 years ago. They weren't. We've been preaching this for a long time. Now the machine tool manufacturers are changing. So, if I'm getting this thermal cracking, if it's in turning or milling, if it's in turning and I have an interrupted cut, turn off the coolant. If it's in milling, turn off the coolant. If I can't turn off the coolant, I need a tougher grade of carbide, which means it has more cobalt. Cratering. This is another photo. Doesn't that look like a crater? Now cratering actually happens on the rake face, where that chip is raking across the surface of the cutting tool. High heat, pressure, and an abrasive wear will wear this thing out. This is where the insert has actually dissolved into the chip. This is that's a small crater. That's one right around the nose. That's another one around the nose. You'd see it a lot of times around the nose because that's where all the heat is. The way to fix cratering, is a stronger insert geometry, reduce your speed. Everybody uses coated inserts, but this is chemical vapor deposition. It's a nice thick coating. Or you use different additives in the carbide itself. That's titanium carbide. This is my favorite. This is thermal deformation. What two things does it take to make a chip? Heat and pressure. What do you think happened here? Way too much heat and pressure. Instead of plastically deforming and shearing away my chip, I'm plastically, usually you will not see this. Usually the old corner of the tool's gone. And there's a difference. How many of you, when going through school, you ever had that hard gray modeling clay? Not Play-Doh, but the hard stuff. Imagine taking a block of that in your fingernails and scraping off the corner. If you have plastic deformation, it'll look just like that surface would if you scraped it away. It would have lines on it, like your fingernails scraped it. The reason I bring that up is a lot of times the whole corner of your cutting tool is gone. Okay? Now you got to determine, is it thermal deformation or is it broke? The way to tell the difference is if it looks like I scraped the corner off, it's thermal deformation. If it looks like a rock in a gravel driveway, that surface, it broke. This is just by too much heat and pressure. So the only thing you can do is rainbows are pretty. If your cutting tools look like rainbows, you may be doing something wrong. Here's your sign. Rainbows aren't in cutting tools. You can get a nice little rainbow color around it. That's too much heat and pressure. The only thing you do, go to a harder grade of carbide. It'll take more heat. You could slow it down, but I hate slowing anything down. I could use a sharper geometry to reduce the amount of heat and pressure at the shear zone. I don't like reducing my feed. That slows things down. We aren't doing all 40 slides. We're stopping early. Don't worry, because the pizza's almost ready. We're going to talk about chipping, and chipping's my favorite one because chips tell you where they came from. By a mechanical force. Let's look at this. This you're going to love it. Chipping is caused by mechanical pounding. So I got a chip being formed. This is kind of scary, isn't it? Whoa. Okay, we got lucky there. We didn't get too lucky there, did we? What usually happens when you have that happen? Okay, you break something, right? When you have a force being exerted on this surface, you will see this surface pop off. What I mean, this is a nasty interrupted cut. You know when you walk through that lab, there are guys that we pay to do this all day long. It's called the slotted log test. They're testing carbide. And it's an interrupted force on the rake face, and what it will do is cause that to break off. And the point I'm trying to get at is if your force is coming in this, if the chip is wider in the direction of the force. So if I got a real chip, wide chip here, if I got a wide chip here and a narrow chip, I know the force came this way and popped that off. If I know where the force came from, what can I do? I can change the edge prep and redirect it into here. I can change, it says reduce speed and feed. I don't like reducing those because that's my productivity. What I'd rather do, use a tougher grade. But if I use a tougher grade, that means it's got more cobalt, marshmallow. Does that mean I go faster or slower? Slower. I don't want to do that either. The first thing I'm going to do is try and get a stronger edge. Get an insert that has more of a hone or T-land on it, like this one right here or this one right here. Redirect those forces into the bulk strength, the compressive strength of the tool. If worst case fails, I can reduce my feed and depth of cut, and I could get a stronger grade. But first I'd change the geometry. I can also get a force here, which is going to cause my top to pop off. Again, the chip is wider here. I know the force came from here. A lot of times you get this from a boring bar that goes below center. You reduce the clearance and the top pops off. What do? If I use a freer geometry, like, whoops, threw it away. drawing that one with permanent marker. Huh? It's not the first time. It won't be the last time. So if I have a negative geometry or a neutral geometry like this, I might come to a geometry that's more like this. Okay, if I'm too sharp this way, this could cause chippage in this way, so I might go more negative. Sometimes I can get what we call depth of cut notching. Sometimes you'll see right at the depth of cut line, it'll look like somebody gouged your cutting tool with a file. What's your name? Yeah. Anthony, stick your arm out if you don't mind. I'm not going to hurt you. I promise. Huh? They'll fire me, you know. All right, now if I was doing this, what's this called? Indian burn. Why does it hurt right there in the middle? I'm making friction. I got forces going in two different directions. I didn't really hurt you, did I? You're going to go to sue? Okay, cool. How many of you heard him scream? All right, here's the point. When you get depth of cut notching, what's happening? Typically it happens on work hardening materials. When you get that surface layer that's work hardened, it takes more heat and pressure right at the depth of cut line than it does below it or above it. That localized heat and pressure is just like that Indian burn. It'll just gouge out the tool. You see this a lot in stainless steel, high temperature alloys. What you do there, you can vary your depth of cut. If you're turning, you can also cut tapers. If you're milling, you can vary your depth of cut. And what it does is that spreads that localized heat-treated part or section of your surface up and down on your cutting edge, and instead of wearing one section out quickly, it takes longer to wear out the whole edge. And it looks like a depth of cut notch. It looks like a notch cutting your cutting tool. Last but not least is it broke. See how this looks like a rock surface? It doesn't look like somebody scraped it. It looks more like a rock. That broke. When an insert breaks, usually I tell them it broke. Inserts don't break on their own. One of those other failure modes was typically happening before it broke. Sometimes I get chippage that is equal on both sides. It's not wider here. It's not wider here. If the chippage is equal on both sides of the cutting edge, it typically means something's vibrating. You're getting chatter. The only thing you can do is shorten your tool gauge length, tighten your fixtures down, make sure everything's as rigid as you possibly can. If that doesn't work, you can change your edge prep that we showed you before. You could go from a positive to a negative. You could go from a sharp to either more T-land or home. Last but not least, you go to a tougher grade of carbide. But if you go tougher, that typically means you're going to have to go slower. Maximize your rigidity, tougher cutting geometry, and stronger geometry. All right, real quick. I got 11 slides to go through. I got 5 minutes to do it. All you got to do is give me the right answers. Deal? You think we can do this? Which one of these is flankware? Give you a hint, there's two of them. All right, yeah, if you give me the right answer, everybody's going to say A and D. Anybody think there's another one? All right, you're right. What is B? Thermal deformation. What's C? C? Cratering. There you go. Okay, which ones are flank chipping? That's it broke. That's built up edge. And we say that's the flank, but I'm going to give you a secret here. That is flank chipping. But whenever you see a chip that has straight edges, if you look, this insert is that insert. This is the top. This is that chip at the top right here. What was happening first? Go away. Look. What was happening first? Thermal cracking. Those thermal cracks got so big that eventually it chipped. Does it make sense how one can end up to something else?
Look at me.
Would
got-
you
You got flank wear, then thermal cracking, then chipping.
There's not that much flank wear.
Is there flank wear?
There's a little.
Thank you.
Go away.
No. But, perfect example, if you don't want to
You're
keep an eye on your
fired.
tool failure, good. Keep an eye on your tool failure, bad things will happen.
No, but he's got a point. He does have a point. We
Thank
do
you.
this all the time.
Am I rehired?
All right. Only because I don't want to travel all the time. You do have a little bit of flank wear here, but that's not very much. You do have thermal cracking right here. He's right though. One failure mode, if it goes unchecked, will look like something else. Where's depth of cut notching? A is actually more thermal cracking. It's C. What's B? Greater. What's C? It's thermal deformation. You can see a little bit of deformation and you see the rainbow. Where's cratering? Oh boy. B and A. What's this? It broke. Oh no. Okay, I'm done. Pizza time. Who didn't get a
Hold on, not pizza time yet.
Oh, it's not pizza
All right,
time.
in the back of your books are color photos of tool wear.
Yeah.
It's a great thing to refer to. You guys always
Is it all
have
the
it.
way in the back or is it the back of
It should be in the
analyzing
tool
tool?
failure. Or
So if you look at analyzing tool life, you go to the back of that section.
should be.
Should be a color sheet, 8.5 by 11. One more sheet.
One more. There you go.
One is the first sheet. There's two sheets that go together. The very, very back sheet is troubleshooting. The one in front of it is pictures of the failure mode. There's the failure mode.